Hi, I'm James Verdier, and welcome to the American Institute of Biological Sciences BioScience Talks, which is a forum for integrating the life sciences. On the second Wednesday of each month, we discuss the latest bioscience publications. And as a reminder, if you'd like to read more, point your browser to academic.oup.com/bioscience. For today's show, I'm joined by Steven Mattocks, who's a fish biologist for the Massachusetts Division of Fisheries and Wildlife, and he's also affiliated with UMass Amherst in their Department of Environmental Conservation. Today, he joins us to talk about fish habitat and migration, specifically how dams affect the movements of species that travel between marine and freshwater environments for spawning and other purposes. Let's get straight to the interview. All right, hey, Steven, thanks very much for joining us today.
Yeah, glad to be here. Thanks for having me.
Just to kind of get us started talking, I was hoping you could tell us a little bit about the fish species that you discussed in your article.
Sure. Yeah, this is discussing Clupiidaes and Alocines, which are shad, herring. Those are the main two groups of species that I discussed in this article. However, salmon are also mentioned, eels, lamprey, any anadromous fish that basically migrates between freshwater and saltwater in a way that transports nutrients, food, and contributes to food web and ecosystem connectivity. But particularly river herring, that's blueback herring and alewives are the primary focus species in this study. And those are fish that make annual migrations from the saltwater to the ocean. From the ocean to freshwater. They spawn out in freshwater ponds every year, or in the early summer, May and June. They grow to be about, give or take, 100, 150 millimeters, and then they'll migrate out to the ocean, where they'll spend the next 3 to 5 years reaching sexual maturity. And then once they're sexually mature and spring comes around again, they make their way back up to these rivers and they repeat the cycle and they spawn out in these ponds. Alewives in particular spawn in ponds, whereas bluebacks will spawn in the rivers. And of course, as I mentioned, shad, they'll spawn in larger rivers as well. So these are really small fish, often termed forage fish because they have an ecosystem role in that they provide food or forage or sustenance for other larger species such as striper, bass, pelagic marine fish such as cod and hake, and really globally. So they're a really important fish. They're really underlooked fish because they're small size, but they have a really cool life history and a really interesting story to tell.
Okay, so these anadromous fish, what they're doing is they're spawning in the freshwater. They move down, and 3 or 4 years sort of at sea, where they're growing and reaching sexual maturity, and then they move their way back up. But because they're not, there are more than one age grouping. You do have a migration every year, right?
Yeah, absolutely. Some years are better than others, but they're anywhere from age 3 to age 7 or 8. Is when they do their migration. So it's better to have a wide age structure during that migration. It tends to provide a little bit more robust spawning opportunity for the species as a whole. And that age structure has certainly changed over the past few centuries. But yeah, like you said, there are multiple age classes. Currently, they're a little bit more truncated towards the younger fish, towards the 3 to 4 year old fish, whereas historically they were a little bit older, 5, 6, 7, 8-year-old fish, although we still do see some older 6 and 7-year-old fish. But yeah, that variability in age structure does help the population, and it allows them to have variability in fecundity and production and swimming ability and condition. So yeah, there certainly is some variation there.
Okay, and from an ecological standpoint, you were saying these aren't top level predator fish. They are primarily ecologically important and relevant as prey for other species.
Yeah, exactly. I mean, you can really call these mid-trophic level fish. And, in an ecological sense, their job is to transfer nutrients from lower trophic organisms, such as plankton. These are planktivore species, and they are filter feeders and feed through various aspects of the water column. And then they provide that energy and those nutrients to larger species that are commercially important from an economic standpoint and also from a recreational standpoint. And also just for an ecological standpoint as far as continuing to transfer nutrients and biomass across the globe.
Okay, great. Thanks for the background. And so for the purposes of this article, you were looking mostly at the northeastern United States, right?
Yes, that was our study area. That was where we actually conducted the ground truthing field field research and experiments, and those are mostly coastal ponds in the New England area.
Okay, and I want to talk about the field research in just a moment, but I wanted to talk just a second about New England. Obviously, it's a very heavily human-affected area. There's been a lot of construction, a lot of damming, et cetera. So just kind of what are the fish up against up there?
Well, they're up against some serious challenges and serious obstructions. New England in particular, which is our study area, has a really long history of damming. We've got the first couple dams in New England were 1630 and 1632, and that's the Charles River and the North River in coastal Massachusetts, and thereafter dams rapidly emerged across the landscape, and we have even secondary rivers were dammed as early as 1700, and that includes the Taunton, the Mystic, the ponds at the Parker, Ipswich, Concord. All those were dammed by 1710, and then you have the major dams we call main stem dams, which really block a disproportionate amount of habitat because they're on the main stem of the river. It's like clogging a main artery if you think about it that way. But the three primary dams that come to mind for me is the Pawtucket Falls Dam in Lowell. That's on the Merrimack River. That was constructed in 1825. The same river, we have the Lawrence Dam in 1848, which almost completely blocked off the entire Merrimack watershed. And then, of course, the South Hadley / Holyoke Dam in around 1815. Then, of course, the Turner's Falls Dam on the Connecticut River in 1798. So, the major rivers for spawning for anadromous fish, like the Connecticut, the Merrimack, those were dammed, before 1850. And we don't even have any data before 1850. So if you just kind of, briefly touch on that and think about the impact of that on these fish, it's pretty staggering. But also, to touch on briefly, they also have a lot of anthropogenic stressors such as development, pollution, anthropogenic nutrient loading. So there's a lot of other issues they face as well.
Okay, so I want to get back just for a moment on the timing of these original dam placements because in my mind, which is probably a bad source, I tend to think of dams as having been sort of 20th century infrastructure projects for the most part, but these were main stem dams that were being put in before 1850.
Yes, exactly. And albeit some of these first dams that were constructed were typically of a less sturdy material. They were often rock or wood crib dams. But actually in the early 1800s, they came around with the concrete dams. That was the Holyoke Dam, I believe, was one of the first concrete dams established. But those dams last. They don't get blown out with storms. They're built a lot tougher. And those main stem dams don't pass a whole lot of fish because they're just giant obstructions. They're really tall. They stick out of the water. And of course, the fish passage systems back then weren't there. And when they were there, they weren't really effective.
Okay, and now I've got to ask, a question that probably has nothing to do with fish, but why were those dams placed?
Well, it's a good question. The really early dams in the 16 and 1700s were mainly for saw and grist mills. So they were to cut timber for towns for development and building homes and building town meetings and everyday life. They were really important. And the grist mills were for grinding corn and wheat and other grain to produce food for the town. So if you imagine yourself as a European explorer coming to this new bountiful land for the first time, you're going to need wood, you're going to need food, and you're going to need some sort of power that's a little bit more effective than horses, say. So those were the early dams, and they weren't too destructive because a lot of them were, say, wood mill dams and rock dams, and the type of dams they were, such as overshot or undershot or breast wheel, allowed a little bit of gap. So there may have been some fish passage there. Probably not a lot, and that's really hard to quantify the amount of fish passage on those really early dams. But then the later dams were constructed for large hydropower, especially when electricity came around. And then also they were developed for flood purposes and all sorts of other things. But yeah, hydropower, flood, and then of course you also had the larger manufacturers when they started doing brick manufacturers, textile mills, producing hardware, iron forges. There were all sorts of industry, and New England's at the heart of the Industrial Revolution, mid 1800s. So you can really see how these dams influenced our past.
So it seems like one of the questions and challenges with all this is the fact that, like you said, you have this major effects occurring to the ecosystem before your data begins. So there's no good baseline information on how many anadromous fish there were in 1500. We just don't know.
Exactly, and that's one of the major problems. If you Google American shad landings in the U.S. or river herring landings in the U.S., you see a nice chart, probably produced by NOAA or some other state agency. But you see the data starts around 1950, and there's some data before that, but it's difficult to actually get the reliable, consistent data that's collected in the same manner. So yeah, if our reliable data starts in early 1900s, mid 1900s, but our habitat loss and significant fishery impediments began much earlier than that, we have a huge problem because we really don't know where the fisheries stand today. So that's kind of what this paper is trying to address, is where were we? We know where we're at now. There's a lot of evidence on that. Where were we, and how far away from our goal are we really? So it's very interesting, and it's kind of overwhelming when you think about it all and actually look at some numbers. But yeah, that's what we tried to address.
Yeah, that's enormous because we typically can think of shad and herring landings being greatly depleted since the initiation of high quality data, but it's actually far more severe than that. What did you find? How do you come up with that sort of estimated baseline?
Well, it's tough. So, I mean, I guess to put it simply, we asked the question. So I guess I'll get back to the point where herring are produced in ponds. So we can think about each pond, each lake producing a certain number of juvenile river herring that then goes on to contribute to the population. So with that in mind, we can ask the question, if this pond here produces this many juvenile river herring, how many juvenile river herring will be produced if all the ponds are open, if all the lakes and rivers are open access? How many herring can be produced then? And there's some difficulties with that because a lot of the systems today are obstructed, as you mentioned. So there are some challenges with that. But with our field work, we sampled juvenile herring in 20 ponds throughout coastal Massachusetts, and they all have a wide range of habitat types and access and depths and all these sort of different geographical and physical differences. But this allowed us to capture a wide range of variation to kind of give us an idea of what these ponds do produce in terms of numbers. And then we basically applied that to historical habitat that was intact before damming occurred. And then that allowed us to get at some estimates of historical populations.
So you went back and you looked at more or less intact ponds and intact habitat. Then how do you extrapolate from that intact habitat out to the broader historical habitat, and what did you find?
Well, the first step in addressing that question was calculating the habitat loss with the timeline of dam construction. So that was the first part of this project. So that was basically looking through town histories, through county histories and historical maps and all these history books, and that took quite a bit of effort. But we basically tracked habitat loss in terms of dams. And what we found basically was that most all the watersheds in New England, that's basically from Rhode Island and Connecticut all the way to Maine, were significantly obstructed by 1850. And by 1900, I think the average percent lake and percent river habitat remained varied between like 5% and 20%, depending on which system you had. Coastal Massachusetts had a higher percent, about 48 or 50% of rivers and streams are available. That's mostly because of intertidal creeks that are likely not used by river herring, potentially bluebacks though. But that was the first step. And then we used some growth rates and mortality rates and length and biomass measurements from other state agencies and research groups to kind of help us produce these estimates of historical fish. But basically in the paper, we highlight a range of estimates of historical biomass. And, the lower estimate ranges from, 290 billion adult spawners that were historically there. And that's much lower than current numbers. And then we have estimates as high as, 2.2 trillion tons of freshwater forage before dams occurred. And then after that, we have an estimate of like 13,000 tons. So it's significantly declined. I mean, our estimates are very conservative estimates, are about 6.7% of historical capacity in terms of river herring. And it's likely much lower than that. We use a lot of conservative estimates, as I said. But the good thing is we do produce a range of estimates. So we basically lost a lot of fish, and we do calculate that in terms of freshwater forage. And that's, again, those juvenile fish. We also calculate that in terms of marine forage, as in 2-year-old, 3-year-old, 4-year-old, 5-year-old, and 6-year-old adult alewives that'll be in marine systems available for other predators to consume. And then we also calculated it in terms of adult spawners and marine-derived nutrients, which will be 4-, 5-, and 6-year-old fish.
Okay, and so this may be extrapolating too far, but is it fair to estimate, how that reduced biomass might have had an effect or might be having an effect on present numbers of larger predator species?
Absolutely. We see that lost prey is a significant problem for many predators and ecosystems. We see a decreased condition in striped bass that's linked to the loss of herring and shad, and this is very well documented throughout the research. Loss of prey is a big problem for trophic cascades. You have predators that are looking for food, and an interesting study by Ted Ames actually highlighted the predator movement of cod and hake in the Gulf of Maine, and he shows that these predators, kind of follow herring runs, and they time their movements to kind of hang out on the mouths of these rivers as these juvenile herrings outmigrate to the ocean. So you have movements and numbers of juvenile herring, which are prey, that affect the movement and timing of movement of larger predators, such as cod and hake. And these fish are extremely important for recreational and commercial and economic purposes. But we've seen larger predators decline in numbers as a result of loss of prey, and this is well documented. Of course, predators have other stressors such as overfishing and pollution and other things, and lack of recruitment. But certainly, it's a huge issue. Everything needs to eat, and there needs to be more biomass on the lower trophic levels to support higher trophic levels.
Okay, and so we've done a lot to devastate these populations, and it's had wider ecosystem effects. I guess the next question then is sort of, what do you do if you were in a management role and were seeking to restore some of these populations and ecosystem function? What would be the logical moves? Were you able to address that at all?
The best move, obviously, is to remove dams. That's the first option. That's where you're actually fixing the problem. A lot of management decisions and a lot of actions recently have been, fish passage systems I briefly touched on. There's some very creative systems like fish cannons, and at Holyoke we have a fish elevator. They're all fancy and cool and, have great engineering and technology, but, they're not a solution. I don't see those as a solution. I see those as a quick fix. And oftentimes you see agencies and investors focusing on the actual fish passage rather than the larger scale implications of the dam. So not necessarily the fish passage system itself, but they're focusing, or they should be focusing on rather, the location of the dam, the size of the dam, and the species it impacts. And that receives very little attention. So back to the question, dam removal is the first solution. And it's created a cascade of problems. But it is doable. It can oftentimes be expensive, which is a problem. Dam repairs are often more expensive, so that's a trade-off. But yeah, we see when dams are removed, we see fish come back, and that's a really optimistic way to look at it. And it's true. We see the Penobscot River dams removed in 2012 and 2013, opened up 1,000 or so miles of river back for spawning, and we see the next year we see hundreds of thousands of fish coming back that were not there. So dam removal works. Most of these fish have a degree of straying from their natal stream, so usually about 10% or so of the adult fish that are returning back to the system stray to a new system, and this allows them to recolonize new habitat or recolonize old habitat. So dam removal works, especially for a lot of these anadromous fish in the U.S.
Okay, and on those dams, who are the natural sort of opponents of removing them? Are these hydropower dams that are incredibly useful and providing a lot of value, or are we looking at sort of artifacts of prior grist mills and things like that?
Yeah, a lot of them are hydropower dams and are currently being used, and some of them do provide a significant amount of power to the power grid. So we have these larger dams that do provide renewable sources, albeit they're not renewable for fisheries and biological creatures, but they are renewable in terms of not burning fossil fuels. So we have that kind of conundrum there, which we can talk about later. But some of these smaller dams, especially in New England, when you have these dams that were built in the 16, 17, 1800s, a lot of them are dilapidated and not being used. So a lot of these aren't even documented in databases that we use. So yeah, a lot of them are just there and just relics, and some of them may allow some fish to pass. But the real challenge is removing these with money. Investors should really consider the cost and the long-term cost of benefits of dam removal and dam construction, especially on certain rivers that are contemplating dam construction, such as the Mekong and other larger dams. But in the Amazon region especially, there's a lot of dams being proposed, and most of the tributaries to the are dammed. And then the other thing to think about, especially not necessarily in the U.S. but in other countries, these large river systems that are being proposed to have dams on them provide a significant amount of protein in fish for natives, and these dams significantly jeopardize the future fisheries for these locals that are relying on these fish. They also can flood upstream habitats when they create the impoundments. All dams do that. They have increased evaporation. So when you have other impacts like climate change, they kind of compound it. So the investors, the management agencies, people making decisions and investing in dams need to consider all of these aspects before the construction, not just the supply of power. We have alternatives that are coming, like solar, that could potentially be remedied with this.
Yeah, I mean, it sounds like a situation in which it would be the easy calculation is to go, this is the cost of initiating the dam, this is the amount of electricity that it will produce, this is the current price of electricity, and this is therefore the benefit. But it's probably harder to make reasonable estimates of, this is the loss to the local population of their food source. This is the potential commercial or recreational or tourist lost money. Those numbers are harder to come by.
Yeah, exactly, and it's hard to comprehend a number like that. So like in our paper we put, we use trillions of tons of biomass, billions of biomass, hundreds of fish. It's hard for people to comprehend that, and you can see how they say, what does that mean? So you're right. It's really difficult to put numbers on that and to really understand the impacts of it. But it's something we have to think about, and that kind of goes back to ecosystem-based management, where we have to consider all the aspects of fisheries. Every other species in the ecosystem is affected when we make a decision, such as building a new hydropower dam.
Yeah, those estimates are really hard to make. From a local example, I'm in the Hampton Roads area, and we've had a lot of consternation and hand-wringing and difficulty over which fisheries to keep open for which periods of time, and sometimes conflict between agencies and stuff like that. It really does seem like a hard problem.
Yeah, and the management agencies that are responsible for putting limits on those fish have enormous pressure from investors and lobbyists and commercial and recreational industry. They have constant pressure to keep those fisheries open. So when you combine that with limited prey resources for those sport fish, you have a big problem. And that's sort of the story of fisheries management in the East Coast. You see, a lot of failures. You see a lot of resilient, positive stories as well. But overall, we could be doing a better job. And back to dams, I'll make one last point that part of future planning for dams. One way to look at it, I think I saw a talk on this, and they were proposing sort of this way of thinking about river networks and systems is all connected. And you can have a few dams. It's okay to have one or two dams potentially if you're having a significant benefit to people nearby. But when you dam every river, that impact is much harder to justify. So if we're smart about which dams we keep and we're smart about which dams we remove, we can significantly increase production and increase connectivity with ecosystems.
And how challenging is that? I'm thinking about New England, and there's a bunch of states up there. And so, do you have challenges with the varying local jurisdictions, or is this, sort of managed from a more central view, or is that a difficulty?
Yeah, it is. Most of the dams are commissioned with licenses by, they go through a FERC relicensing process. And those processes are only about 30 to 50 years. So the Federal Energy Regulatory Commission will permit these licenses to operate these dams for such a long period of time that if something happens between them, you can't decommission the dam or you can't change regulations. So there's a few that are actually up for relicensing right now. I believe it's the Turners and the Holyoke, and state federal agencies are working together to kind of get the regulatory aspect of that right, including Mass Division of Fisheries and Wildlife. We're working with U.S. Fish and Wildlife Service to kind of really figure out and fine-tune what needs to be done in order to keep flows and to keep the habitat suitable for most of these fish. But yeah, when you have such a long period of relicensing, it's kind of daunting to know that these dams will be in for another 50 years before they're reevaluated. So it's kind of a crazy process to think about, but we do have lots of organizations that are working together, and a lot of my colleagues from UMass and state and federal agencies that are working together on this. But it's a lot to consider. You have to at least understand it from the dam's point of view as well. They're providing energy to a large number of people. They control floods and have other aspects of the river. So it's a really tough situation, and it's a lot of political and administrative aspects to it that are kind of above me.
One question I often ask, and I think we're probably about reaching the time, is the question of climate change, because it's ubiquitous and it's something that has an effect on every system that we talk about. So how does climate change affect these fish, and how does it affect your research?
Yeah, climate change is a hot topic, and there's really compounding effects when you think about climate change and the alterations to ecosystems that it brings upon. There's a lot of evidence out there that shows that anadromous fish are highly vulnerable to climate change, and that's mostly all anadromous fish species. And one of the reasons for that is their limited migration routes due to these dams. We have compounding effects with dams, climate change, and other infrastructure. But if you can imagine these fish upstream of dams or downstream of dams, or just trapped in between 2 or 3 dams, and you have warming temperatures upstream and downstream, the main problem there is these fish do not have the ability to migrate to more suitable refugee habitat. So that's a really large issue that really contributes to the high vulnerability of these fish. There's also a ton of evidence that increased temperature decreases salmon lipids or condition. Temperature changes the life history of these fish. It alters the proportion of resident and migratory fish, and they basically, with climate change, we'll continue to see increased variability in water flow through these rivers. So basically, it'll change the timing and magnitude of flow. So it's more difficult for these fish to be able to hone in on their spawning times and spawning locations if the rivers are more variable, or if they're not behaving as they did historically. So that includes more rainfall in the form of rain rather than snow. But yeah, so the main one is the compounding effects of climate change, warming temperatures, lack of migration routes, and then you have continued pollution and overfishing. It's kind of building up to be a really difficult situation for these fish that need to move around. They need to be able to stray to new habitats when we're constantly jeopardizing the habitats they're currently in.
That sounds like a substantial set of challenges. I was hoping you could tell us a little bit about what's up next for your research. I think you mentioned in our email correspondence that you're out in the field right now. What's up next?
Yeah, well, actually, right now I'm with Mass Division of Fisheries and Wildlife, as I said. So we're working with U.S. Fish and Wildlife Service, and we're doing a juvenile shad project where we're trying to calculate the abundance and density of juvenile shad in the Connecticut River. And that's really cool because this is a somewhat understudied river. There is some good data on it with the dams. There's a lot of data that's collected with the relicensing and studies and stuff. And there's some good data, but the same idea as this paper is calculating the density and abundance of juvenile fish can tell you a lot about the adults. And the relationship between juveniles and adults is not necessarily a linear relationship that's easy to graph out and understand. It's pretty complex. These fish can be density dependent. So you have to kind of really be clever about how you model and how you predict the number of adults from the number of juveniles. So this is a really cool project. But what's also interested me is looking at predator fish condition with the juvenile densities of fish. So right now I'm finishing up another project with folks from UMass Amherst and Adrian Jordan, who is my advisor there, looking at the condition and growth of white and yellow perch with varying levels of alewife density. That's juvenile alewife density. So we did a very similar project where we measured the density and size of these juvenile alewives with perch seines in ponds around Massachusetts. And simultaneously, we captured adult yellow perch and adult white perch, and we took them back to the lab and we weighed their livers and took all these indexes of condition to figure out how healthy they were, how much fat they had, how many lipids they had. And then we also looked at their growth. We aged them using their otolith, which is their ear bone. And you can basically, like a tree, you can count the rings and see how old they are. So if you have a length and an age, you can kind of get a growth rate to see how fast they're growing. And interestingly, what we're finding preliminarily, what we seem to be finding is that both perch grow faster in early ages when there's more juvenile alewives. It makes sense. They're feeding on these alewives. We've documented that in this paper right here. And not only do they grow faster in the early ages, they have significantly increased condition or overall fitness or health is one way to look at it. So if you think about that on a large scale, as discussed in this paper in BioScience, you can really imagine that it does affect the predators. And this is repetitious in a way that we've already discussed the striper condition decline with lack of prey. So this isn't new, but really quantifying it for freshwater predators is new. Herring are typically thought about in marine contexts. I mean, they're thought to contribute to marine predators, which is true, and they're very important to marine predators, but rarely are they studied in freshwater systems, and that's kind of what we did. And these results are really interesting.
So it sounds like you're getting into a really interesting level of granularity there, where you can examine the abundance of this herring species and find out something about the fitness of the predator species.
Exactly. Yeah, it's really cool to look at that. Especially when they're direct predators. But also, we're doing some stable isotope analysis to really fine tune the food web configuration, and that really helps us understand the connectivity of these trophic levels. So, you have the perch, you have the herring, and then you have the plankton. And we actually had an undergrad look at the plankton as well. And as previously noted in other research, plankton communities are significantly altered by these herring as well, due to predation and filter feeding, as discussed. But so you can kind of start to imagine that these pond ecosystems are significantly altered by herring. So these herring alter the systems, and then they themselves are altered. With landlocked herrings, we see changes in physiology from these fish. In landlocked alewives, we see smaller alewives. They have thinner peduncles, longer heads, slower growth, and even earlier age at maturity. And we find that those even can change the structure of the prey and predators. So it's interesting to kind of fine tune, like you said, all of these little aspects of trophic ecology and food web structure within one system. And we can compare those systems, and that's what we did in the study I was mentioning. We actually looked at 28 ponds rather than 20, and we looked at those from Connecticut all the way to Maine as well. And we're finding a very similar spike in condition from perch with that. So it has implications for management. It has implications for reiterating the fact that if these dams come out, seasonal pulses of these anadromous fish can just really supply these predators with a reliable source of forage that they really need to get them through the winter.
That sounds like fascinating research, and we'll look very much forward to seeing more of it. Thank you very much for joining me today.
Thank you for having me. It's been a pleasure.
And that concludes this episode of BioScience Talks. Just a reminder, the journal BioScience is published by Oxford University Press on behalf of the American Institute of Biological Sciences and is made possible by the support of our members and donors. Thank you, and talk to you next time.